This is my third class. Let me just get rid of this chair. And as I mentioned in the first day, I'll be talking about the interplay between topology and correlations. So I'll start talking a little bit about topology and topological properties. Velasco might recognize these view graphs. They are from his supervisor. You can tell him not only that I use, but I also give him credit for that. So he is the expert at UFRJ on topology. I am kind of new to this field, so I ask the knowledgeable person nearby for some help. So the idea is that topology can classify objects that cannot be smoothly deformed into one another, and this is something you can see in this drawing. So you cannot change a knot into a donut smoothly. And in some other instance, you see that you can, like you can change the donut into the mug. They both have one hole, but not into the sphere. So we can think of a way of characterizing objects with some property. Here, the property is the number of holes. In one case, 1, and in the other case, 2. And this gives information about the topology of the system. We can also think that if we have the number 0 associated, we are going to mean that this is a trivial, non-topological phase. And you can go from one trivial system to a topological system by changing some properties in your system, and we are going to look into some cases. So materials and topological states of matter have been studied a lot, and the amount of studies that are going on this field is fastly increasing. There are many different materials in which we can see topological behavior. I am not going to cover it all. I'm going to cover 2 different systems that I'll come into in a bit. And I found that this thing here, I thought it was really curious. Microsoft released a chip and called it Majorana. From all I heard, there is no Majorana involved, but the name has become so, trendy and a buzzword that, even the chips are getting this name. So I'll start talking a little bit about the Haldane model, and the reason will come clear in a moment. The Haldane model is described by this Hamiltonian. So it's described within a honeycomb lattice. We have regular hopping between near neighbors here. And between second near neighbors, white to white or black to black, we have a hopping that has a complex phase to it. And also in sites A and B, we have either in A or B, here in A, an on-site energy. And the phase diagram was found by Haldane, and it looks like that. So the 0 region here outside is a non-topological region, and we have 2 topological regions within here. And when he wrote this paper, this is a piece of the introduction. While the particular model presented here is unlikely to be directly physical realizable, so he thought that this was something, curious and interesting, but not realizable. In 2014, within optical lattices, Tillman-Esslinger's group realized the exact same model, and here are, the lobes that have the topology phase within. And so I mentioned in the first class that optical lattices was an interesting platform to study condensed matter physics, and this goes beyond only, strongly correlated systems, but topological systems are also being studied here. So how can we say a given state is topological? So the usual prescription is we look into a topological invariant, and how do we get that? So we get the Hamiltonian in K-space. we get the wave function by diagonalizing it also in Kent space. We calculate the Berry curvature, we integrate it over the Brillouin zone, and this gives me the Chern number, which is a topological invariant. If it is 0, it's non-topological. If it is non-zero, then we have some topological state. So what happens when interactions are present? Usually, we don't have a Hamiltonian in K space, and we don't have psi of K, and then we cannot get, you know, the topological invariant. So what should we do in these cases? So this is my first attempt to look into what happens when we have both topology and correlations, was to look into a very simple model, which is the Sushri-Verheugen model. So the SSH model, this is a sketch. We have two kinds of sites, the even ones and the odd ones, and they are connected through a hopping that is alternated between t plus delta t and t minus delta t, and this is a non-interacting Hamiltonian. So we solve this by using numerical, like brute force diagonalization, Lanczos to extract the ground state. And we did this with open boundary condition. And we also use a twisted boundary condition. I don't usually mention a lot about the numerics I do, but when we are dealing with a small system, and Lanczos method only allows for a small number of sites, it's very interesting to use twisted boundary condition, because then we can average over the different operators with different boundary conditions, and this is like you are filling the Brillouin zone with more K points, because you have different allowed K vectors as you change the boundary condition. So this is numerically good to extract data when you're dealing with a small system. So this is what we found. So this is the energy as a function of dt, the hopping hopping variation. And we can see here that when dt is negative, we have these edge states here. So when it's red, the states are in the edge within the Fermi level. And when dt is positive, then we don't have the states. So it was already known that the SSH model has a topological state for negative dt and non-negative for positive dt, and that the phase transition was in 0. So we are just, you know, getting to know we are doing something that's okay. And so we looked at the gap, and here we use different system sizes to probe finite size effect, and we see that the gap actually closes at this symmetric point, and it's non-zero outside, so we have an insulator in both sides. And also, we calculated the winding number that's obtained this way is like the sum within the Brillouin zone of the argument of this quantity here. And we see that for negative dt, the winding number completes a loop here within the Brillouin zone. And in the trivial phase, it doesn't. So this is another way to look into the topology of these systems. So what happens now if I turn interactions on in this model? So then we added this term here, which is a near neighbor interaction V. And so I just forgot to mention in the beginning, but this is a spinless Fermion problem. So I only have one flavor of electrons or particles that have no spin. So the questions that arise when interactions are present is basically what happens? What's the role of interactions? Does it change the topological phase? Does it enhance, decrease? And how do I characterize it? And in a more broad sense, what is the phase diagram now that I have another variable besides dt? So we started looking at the structure factor, the charge density waves. It's natural. We've seen this maybe yesterday or, yeah, yesterday, that we had, whenever we had near neighbor correlations, we tend not to have particles in near neighbor sites because you pay an interaction V. So you have some charge density wave forming when this V factor is increased. And this is what happens here. This is a heat map of the structure factor. We see here in the blue region we have an enhancement, and in the red region not so much. So as V increases and it's positive, we do have some charge density wave formation. And we know the system very well. We know this is in the Ising universality class. So we can do a collapse knowing the scaling function because we do know the exponents from the Ising universality class. And the fitting looks pretty good as we have different system sizes, and we extract the critical V to entering the CDW phase by this scaling. So this is for a given value of dt, point -5, and then we repeat for all the values we have. And we have, what I'll show later, a phase diagram from where the critical charge density wave is starting. So another diagnosis quantity we have calculated is the von Neumann entropy. So the von Neumann entropy measures the entanglement, and we divided the system into A and B. So the A is the odd lattices and the B the even lattices. So we traced out all the odd ones and remained to probe the entanglement between one and the other. So, and this is what the von Neumann entropy looks like. It has an interesting behavior here with a peak in negative values. So this is the heat map. This is where the first peak is. But for the positive region, we don't have a peak. But if we take the derivative with regards to V, we see it has a minima. The minima changes with system size, and we carefully did a scaling analysis to find the critical value. So the von Neumann entropy signalizes two phase transitions, one here and another one up here. And the color code is for the intensity. So here is where it's larger, and here it's small, and here it's small. And the pink stars here are obtained from the Jordan-Wigner transformation, so are exact values of a transition. We also looked at the energy gap. So this is for a chain with 20 sites. And we see we have a gap here and here, but all the other regions, it goes close to 0. So it's a metallic region here, and here insulator and insulator. Once again, we are dealing with small chains, so we have to worry about size effects. And we did, once again, a finite size scaling analysis with different system sizes to pinpoint where the transition actually is. So here within fittings with inverse system sizes. And to finish up, we looked into a topological marker. So when dealing with interacting systems, it's hard to find, how do we probe that the state is really topological. Edge states are a hint, but not necessarily mark the presence of topology or a topological state. And we have collaborated with Shen Wen from PUC, the Catholic University in Rio, and he had proposed before a topological marker that's based on a wrapping number. So the wrapping number, as I wrote here, because I needed to cheat because this is different for me, so it's the number of times the Brillouin Zonus torus wraps around the target sphere of the Dirac Hamiltonian. So this is somewhat similar to the Chern number that you have a wrapping around something, and the number of turns you give marks whether you have topology or not. So he had this idea to write the wrapping number into projectors of valence and band states. And he claimed that this was applicable to any dimension and any symmetry class. So we got his topological marker that looks like that. So here Z is the Pauli matrix. P is the ground state projector, looks like that. Q is the projector onto the excited state, so every state but the ground state. And X is the unit cell position operator. So this is his proposal to write the topological marker. And after some manipulation, we found that this P matrix elements could be written in terms of the Green's function, and the Q into 1 minus the Green function. And so the final form we use it is this one. And his expectation, so he had done this in a non-interacting system, and he saw it worked, and it went from 0 in the non-topological phase to 1 in the topological phase, and the transition is very abrupt. As soon as you enter the topological phase, it turns from 0 to 1. And he had expected that this would be the same here in the interacting system, but this is not what we saw. We saw that by when correlations are present, the marker goes from 0 to 1, but smoothly, not abruptly as one would want. But anyway, so this is what it looks like. We also calculated the ZAC phase. This is some normalization constant. We are able to get that because we get the ground state for different phases L, so we can integrate varying L from along different phases. And so what we see, the black line here is the ZAC phase. So it is 1 in the topological case, and it goes to 0 as soon as we enter the non-topological phase. But here we have the topological marker, and as this is a quantity that depends on the site, we have calculated it at site L equals 4. So the total length of the chain divided by 4. Not to be in the border, but not in the center. And so this is what it looks like. For a small system, it changes more smoothly. But as we increase the system size, it approaches the ZAC phase behavior. And here we see another thing. This is when we see the variation with delta for a given value of V. And this transition is much more smooth when we consider a fixed delta and varying V. But anyway, we've picked up, there's this point where all the different system sizes closed and change. And this is very close to half. And so we picked up this point as our point of the transition. And with that, we come to this phase diagram. So, yeah. Sorry? The what? I don't really know. We don't looked into that. Yeah. So let me go back. So here we can have both repulsion and attraction. Here we are considering only, in this case, repulsion, but we considered both. So we have, yeah. Not here, but we did look into that. Yeah. Yeah. So I think if I do remember right, it's symmetric for delta t equals 0, but it's not if we move sideways here. So this is the final phase diagram we have reached. Here we have a charge density wave system, so with some charge ordering here. In this region here, we have an insulator, but different insulators in each side of the DT. For negative DT, we have a topological insulator. For positive DT, we have a band insulator, and here we have some phase separation states. These lines here are obtained with the help of the topological marker and with the help of the gap, where the gap goes to 0, and as well as of the topological marker. So, questions this far? Yeah.
The entanglement entropy, you also use the entanglement entropy
Yeah.
as a marker?
Yeah.
But my question is more like, why does the behavior of your entanglement entropy tells you that you are in a topological transition?
So it's a very good question. So the entanglement entropy, it signals a phase transition. So it could be to a topological state to a non-topological state, or to a topological state. So the presence of some sort of a maxima or a minima, or the minima of the derivative in the entanglement entropy only tells me I have something going on, and it's very likely to be a phase transition, but not the kind of phase transition. So to be able to claim it's a topological phase, then we have to go beyond the entanglement entropy. Yeah, so we didn't look into that. We looked into the A and B sites, but probably if we looked into the... Yeah, well, usually when you get entanglement in this scenario, you cannot take two sites and leave all the others, because it's a bipartite entanglement, so it's one block and the rest, and so you cannot do one end and the other end, one edge and the other edge. So that's one problem.
Hi. In the Schiffer-Higger model, you have the breaking of a symmetry that marks the transition between the topological phases, because you break the symmetries in the crystal. But in this case, if I am understanding, you have the same, but this breaking of the symmetry is smooth or something like this?
Oh, I wouldn't say that it is smooth. I would say that the topological marker has a smooth behavior, but that doesn't mean that, the behavior itself is smooth. It's that maybe the topological marker is not as sharp as we would like, and it's very size dependable. So when we have broken symmetry, it usually happens in the thermodynamic limit, not for the small chains we have. And we have seen that as we increase the chain size, as I've as I've shown here. So increasing the system size, reaching 20, I get closer to a discontinuity and a more sharp behavior than for L equals 8. So it's a size effect that happens because, I can only do a certain size of chain.
Thank you.
It's like an order parameter or something like?
Yeah, so...
it's because it's not like a sharp that you're not calling order parameter, because it looks to me like it's...
Yeah, I wouldn't know how to answer the question. I am not sure it's an order parameter, because when you have something you call a marker, it's like the von Neumann entropy. It's not an order parameter. It's something that signals a phase transition and of the topological kind. So I wouldn't say it's an order parameter.
Okay.
Yeah, maybe a comment on the smoothness. So what I think happens here, I mean, if you just take the non-interacting Su-Schrieffer-Heger model, and the reason you can define a winding number, right? Because this like mapping that you said, like how much as you go around the Brillouin zone torus, basically if it wraps around the Dirac sphere, that is the Chern number. And now if you go to one dimension, your Brillouin zone torus is a line. So actually you need further symmetries to define the topological invariant. So you can look these up in the tenfold way, and then you see that in order to define a winding number, you need chiral symmetry on the level of Hamiltonian. That just means you don't have a Pauli Z. I mean, you have only two Pauli matrices. So you don't have a Dirac sphere, you have a Dirac circle. And then you can make a mapping. Then you can walk around your 1D Brillouin zone and ask, does this, on the qubit, does it go along the Dirac circle? Now, what happens if you put interactions and the chiral symmetry is kind of like fine-tuned? I mean, I guess Su-Schrieffer-Heger it's the simplest model, but it's kind of like an emergent symmetry. So a random perturbation would break it. So here, if the interaction would break this chiral symmetry, then this topological invariant is not well defined. And you don't have a winding number, but like it becomes a 3D problem. And you can imagine that like this winding like lifts slightly out of the plane. So like I think this is what happens here, that you don't get a quantized response anymore. So it's kind of this kind of like smooth thing.
So what you're saying is, if I repeated this in 2D, not the Su-Schrieffer-Heger model necessarily, but a 2D topological phase, then the sphere would be better defined, then I would see a sharper thing?
So it depends on how you do it, right? I mean, these kind of like things, they all represent two kind of like families of matrices. So you kind of like always need to, if you kind of like if you want the state vector at a particular k point, then you need some renormalization scheme that makes it a free theory again. And it turns out that actually, and that's like a pedantic detail, but like I know the many-body Chern number in 2D. This is slightly misleading because it's not formally the same topological invariant. It's the topological invariant is the Chern number for free theories is a Z invariant, and you have more information if you do this twisted boundary trick for a single interacting wave function in 2D, but it turns out that the Z part counts the number of edge modes. So I think it's a fair comparison, but it's really hard to kind of compare these two in general cases if it requires symmetry, that is.
Okay.
Sorry,
Thanks. Can I move forward? So I'm now, I'll talk about another system. And once again, the idea is there another way to probe if I have topology in the presence of correlations? And usually things to look at, edge states are kind of a hallmark of the presence of topological states, but having an edge state is not, will always happen when I have a topological state, but is necessary but not sufficient condition. And some sort of hidden order or what else? So I'll turn to Haldane again, and I'll start to discuss his conjecture for spin chains. And so Haldane made this conjecture a while ago. If we have integer spins or half-integer spin chains, their behavior is very different. So when we have half-integer spins, this is what happens. We have some level spacing here, and the level spacings decrease as I increase my system L size. And in the thermodynamic limit, I don't have a gap. And this is what happens for half-integer spin chains. On the other hand, if my spins are integer, then something else happens. I have what has become known as the Haldane gap here. So let me blow up this figure a little bit. So here is my ground state. Above it, I have this blue state here, which is actually a triplet. It's what we call the Kennedy triplet. And above this, a huge or a Haldane gap, a sizable that doesn't go to 0 in the thermodynamic limit. And here, these states, all the triplets, all the states in the triplet are marked by the presence of edge states. So there is a recent experimental realization of this system, once again in optical lattice. This is a tilted edge ladder. So it's a ladder in which it's kind of you pull to the side, and you have a next, a spare, unaccompanied side here and another one here. So you have a regular ladder in the middle of the ladder. His ladder, the experimental ladder, is not too big, not that many rungs. And you have an empty guy here and an empty single guy here. And this behaves more or less like a spin-1 chain. And if you don't pull these guys to the side, then it doesn't behave like a spin-1 chain. And so the difference here, he actually measured edge states. So there are some border states here, and tried to look into some hidden order string correlator, and characterized some topological state in this case. So a related model to this is the Heisenberg ladder. So this is the Hamiltonian. It's a ladder where you have exchange interactions along the rung, along the leg, perpendicular, and some diagonal. And also you have a Zeeman field here. So I'm not interested with what happens in the Zeeman field. So this phase diagram, the Y is the Zeeman field. I'm only interested in what happens here. And when you have the symmetric case that all exchange interactions are the same, you have some Haldane phase here when J perpendicular is over J is smaller than 1.41. And so this is what has been observed in numerical simulations some 20 years ago, 25. So we decided to study, we used the Emergent to study the Hubbard ladder, but our ladder is different than the one in the experiment, as we don't pull it to the sides and have unaccompanied sides out of the ladder. What we have is two legs with perpendicular hopping T perpendicular and a diagonal hopping that we are calling TD, and also correlations. So when we first started that, we thought that this TD would only induce frustration. And so the questions that come out into looking into this model is the Haldane phase robust when charge fluctuations are allowed? So we know they are present in the strong coupling limit where we don't have charge fluctuations, which is the Heisenberg limit. But when I relax this constraint, what happens to the Haldane phase? And when I move away from the symmetry point that the diagonal J is equal to J, or the diagonal hopping is equal to the other hoppings in the system. So I'm starting from backwards. I already give you the answer. Yes, we still have a topological phase. So this is U. And so up here is the large U, and here is the diagonal hopping TD. And so when U is much smaller than infinity, we still have a Haldane phase. It goes all the way down to around close to 5. So the Haldane phase is very robust when we relax the strong values of U. And also we can move to the sides and have TD away from the symmetry point 1 and still have a topological phase. So how did we characterize what happens in the system? We first started to look at what happens when we don't have frustration, when we don't have diagonal hopping. And we do understand it pretty much well. So we have something like that, black and blue and red. So in the different sublattices, we would have spin up in one sublattice and spin down in the other sublattice. So that if we look into interlag near neighbor correlations, it would be negative because they are pointing in another direction. And if we look into diagonal correlations, they are positive because they are pointing in the same direction. And so we looked, this is a heat map of the spin-spin correlation functions here along the rung. And so we expect it to be negative, and negative is blue. And it becomes positive, like here in this region. And the diagonal one, the other way around. So here it's positive, and here it's negative. So we change from an arrangement like that, where we have antiferromagnetism along the X and Y direction, to a configuration like that, where we have antiferromagnetic correlations along the leg, but ferromagnetic correlations along the rung. And if we look into that, each rung is like a spin one entity, because we have two spin halves pointing in the same direction. And this is why the system behaves very much like the spin one Haldane chain. And so we looked at what happens at the diagonal spin correlations, and we see it's positive and it's negative, and it reaches the Heisenberg value here. The Heisenberg value for the spin one system has been known for a while from White and Hughes. And so this is truly reaching the spin one system. And if we probe the antiferromagnetic in the size and ferromagnetic structure factor, we see it's intense here and close to zero here for antiferromagnetic correlations, and the other way around. Here is close to zero for ferromagnetic correlations along the rung, and positive and intense here. So this idea supports this sketch that we do here. This for the trivial case, and this is for the topological case, although I've only shown so far magnetic correlations that don't necessarily mean this is a topological state. So after that, we decided to look what else we can see to probe, for topology. And so we looked into edge states. So T here, I should have written, but is the rung. So this is T, this SZ in 0 plus SZ in 1. So this is 0 and this is 1. And this for the same L, for the same site. So if we look at the rung correlation function as it is here, we see that if we follow along this line here and we are in the trivial phase, these correlations go to zero very fast, while within the topological phase, within this region here, they oscillate, they decrease, and then they increase again, which is a marked look of an edge state. And João was able, he plotted the absolute value of it, and it goes down. This is in semi-log scale, and comes up, and we are able to find the correlation length of the edge correlations. And so this is what happens, this correlation length psi. It's very small within the trivial phase, and it kind of explodes here at this border, and then it decreases but stays in a finite value within this dome-shaped region where we have topology. Another thing we looked into is some hidden antiferromagnetic orders. So if we had a spin half, we know what antiferromagnetism look like. It's up, down, up, down, up, down. And that's straightforward to look. with structure factor, we are used to. But in this case, as we have some zeros, because we have a spin one like, we have up, down, up, down, up, down, but with some zeros in the middle. And these zeros in the middle, when I calculate the antiferromagnetic structure factor, they mess up, you know, my calculation, and I can't see what's in there. And this string operator, this part here, it kind of removes the zeros in the middle. So it signals when I have removing the zeros in the middle, up, and down. And we have calculated that. So this is the string operator seen like in half of the L equals 4 as a function of R. And we see here in the trivial phase, it's kind of 0. And here in the border, it increases. And inside the dome-shaped region, it's higher. So we see we have some hidden order within this dome-shaped region. And we are worried about size effect, so we extrapolated this with 1 over L. And we see that if we look into the regular Niel ordering, it goes to 0. But if we look into the string order, it actually goes up as we decrease the system size. So we do have some hidden order within this phase here. We also look at the gap. So this first gap here, we expected it to go to 0. So within the Haldane phase, within the topological phase, this is this gap here, going to 0 as we increase system size. But this gap here, which is the Haldane gap, is robust with increasing system size. So we're seeing exactly what we expected within the topological phase. And this is for spin half systems. We don't see, you know, this vanishing gap and the presence of the other gap. So last but not least, we look at the entanglement spectra. Because when this is one of the markers that is more, I would say, widely accepted when we have symmetry-protected topological states. So the idea is we split the system in half, so left and right, and we write the ground state like that. The part of the left, the part of the right, and here the weights of that. And these weights are what we call the entanglement spectra. And this quantity has very interesting properties. From that, we can extract the entanglement entropy. But this is not what I am mostly concerned about here. I am concerned to see if these guys are evenly degenerate, because this is a strong signalization that we are in a symmetry-protected topological phase. So that's what we are going to do. We are going to probe the entanglement spectra and see whether it's degenerating pairs or not. And also, if they are degenerating pairs and we look at the distance between one value and the next, as they have pairs, this maxima between the different distance will vanish. So we are looking into both. And so I took two different cases. This is in the trivial phase, and this is in the topological phase. And this is what happens as we increase U. So if we look at the entanglement spectra here, red is when we have evenly degenerate case, and black when we don't. And they are all, you know, mixed up. Here, nothing happens. While here, here is pretty messy, but this purple area here is when we have U large enough to be in the topological phase. We see that we start to, the odd degeneracy cases are disappearing, and we only have pairs for the stronger U. Of course, we have size effects here that we are kind of probing into here. This is the the maxima of the entanglement spectra. It's messy, and here it goes to 0 in the topological case. And we see as we increase system size, it really goes to 0. So this is what we found here. We probed that the system has a topologically trivial phase, which is a Mott insulator, for a wide range of diagonal hoppings and a wide range of views. But there is this dome-shaped region here where we have a symmetry-protected topological phase. We are doing something else now, which is like looking to another region of this phase diagram. We've kept, during this work, T and T perpendicular equal to 1 and variety TD. And now we are kind of looking at this line here where TD equals to 1 and looking what happens when we move out of the panel here, perpendicular to it, and let T perpendicular be different than T. And this system has many symmetries that I had no idea before. One of them is if I switch one of the up and down rungs here, the system is in a symmetric, the ground state is symmetric, and this switching operator P here can only have 2 eigenvalues, plus and minus 1. And so the ground states are divided between the ones with up and the ones with plus 1 and minus 1. And this is what it looks like. So this is the P minus region, and this is the P plus region. Now here is T perpendicular, not TD. TD is set to 1 here. But we have this separation here. And what happens in the P minus sector, the spin correlation functions between pairs in the same rung is always positive, while in the P plus it's always negative. So if we look at spin-spin correlations, it's like positive in here and negative in here. And so in the P minus sector, it's not only positive, but it's completely independent on the value of T perpendicular. And it took us a while. We also looked here at the energy, and the energy is also completely independent of T perpendicular within this region. And now we kind of understand why. In this region, we have a configuration of spins that is like that. And we have something like that. We don't expect the hopping, the perpendicular hopping, to mean anything, because we are Pauli blocked, you know, to have hopping here along this direction, because they are both pointing in the same direction. So hopping along the rungs is blocked by symmetry in this the whole P minus sector. And so this makes that quantities like energy as a function of T perpendicular, or spin-spin correlations as a function of T perpendicular, to have no dependency. So it's really curious that when we have when we are specifically in the symmetry point, the diagonal hop that induced frustration actually has the exact effect, opposite effect of kind of wiping out all the frustrations, because when we don't have this perpendicular hopping in here, we regain a bipartite system in which this is positive, this is negative, positive and negative, when we don't have any frustration at all. So this is not by accident, but by symmetry, and we didn't realize this at first, and we really think this is really interesting, and we are still exploring the effects of that. So concluding, we found that symmetry plays a very important role in the systems, and not only because we have a symmetry-protected topological phase, but we are still figuring out what's going to happen in this symmetry point and within this sector. Hopping along the rungs is Paulian symmetry blocked. by this, in this particular point. And the presence of diagonal hopping that induces frustration also induces symmetry protection. So it gives and it takes, gives in one hand and it takes in the other. And finally, I've shown today two very different Hamiltonians that display topological properties. The topological properties are altered by the presence of correlations, but it's interesting. We have to figure out, it's challenging that we need to figure out other ways to probe the topological phase when correlations are present. And maybe this is kind of an invitation. This area of research of topology has had a vast amount of work and increase and enhancement in our understanding in recent years. But still, when correlations are present, we have less understanding. So less understanding means more things to do. And so if it could be an interesting area for, some of you. And with that, I end.
Questions? When you say about the questions there about involving correlations with the topological phases, could you describe in more detail what kind of...
Yeah, I think one of the question is how do we say a given phase is topological? Because when we don't have correlations, this is very well established. If you're in 1D, you get the sec phase. If you're in 2D, you get the Chern number, and that's it. It's very well accepted. But when you have correlations, I was only able to get the sec phase because I was dealing with a very small system. If I had, a larger system, I wouldn't be able to do that. And in 2D, I don't know of people that, are able to get a number in 2D when correlations are present. So how do you characterize, a topological state?
So let us think again, Thereza.